So today we are going to be discussing kind of how CUDA works. A lot of people understand kind of the basics around machine learning, but a lot of people don't understand the engine or machine learning workloads to actually run on NVIDIA GPUs. So today we're going to be going over how CUDA actually works. A GPU can run thousands of these threads in an execution cycle, but still avoid a lot of the latency hits that come with memory stalls. One interesting thing to know about GPUs is they actually have much slower clock rates, and that's kind of counterintuitive because they're built to be these machines that are capable of operating on massive amounts of data. But the way they do it is by hiding the latency through mass parallelism, essentially. Why does performance matter? Well, we don't want to be waiting more than we have to when we're trying to train a machine learning model or when it comes to inference. Let's say you are performing inference on a self driving car. And something that's important to understand, I guess, about CUDA kernels is a lot of them are typically memory bound. Typically, memory is the bottleneck when we're trying to execute at these extremely fast speeds. But the way we are able to, again, hide a lot of this latency is through mass parallelization. Some bottleneck signals that can be picked up on when you are going through your profiling are low ALU utilization points. High DRAM use with low cache hit rates would infer that you need to coalesce your memory accesses. Also, having a low occupancy of your streaming multiprocessors can prevent you from reaching the entire compute capability of your GPU, which is something that you want to avoid. Before we get into kind of the model of CUDA, let's go over some just basic differences of CPUs and GPUs. CPUs are very optimized for low latency. You're able to get a singular instruction done a lot faster on a CPU than you are on a GPU. The difference is on GPUs working on multiple threads. So whenever an instruction executes, that same instruction is going to be executed on 32 different contexts, 32 different threads in the warp. So first thing you have to understand when breaking down the CUDA paradigm is understanding the concept of grids and thread blocks. So each CUDA kernel, you will launch a grid of these thread blocks. This grid can be three-dimensional, one-dimensional, or two-dimensional. And each of these blocks have a predefined number of threads. So in my example launch, we would have a grid with a dimension of 4 and 3. And so we would have 12 blocks, each of them containing 256 threads, which will then create 8 warps from each of these blocks. These blocks are put into a block queue and the hardware schedules them. It's pretty simple. There's nothing super complex at this abstraction level, but something a little interesting happens at the warp schedule that allows us to hide a lot of the latency that comes with global memory access stalls. But the warps at the warp abstraction, if a warp ever stalls, the warp scheduler will actually just schedule another warp. It won't stick on those 32 threads and say we're going to wait until we get the memory we need. We are going to just throw in another warp. This context switching that these warp schedulers are consistently operating in has essentially zero overhead, which is very important because you need this zero overhead context switch to be able to justify your constant switching of these warps to hide the latency with this massive throughput. Another important concept to understand is the memory hierarchy. The registers are going to be the fastest of these 4 different types of memory, and they are going to be per thread. So if you want to, let's say, create a little cache for computing 4 elements in a matrix multiplication, and each thread is going to compute 4 different elements, then using your registers will be a very good use for that, so that you can constantly access these 4 different values, and you don't have to go to shared memory or L2 cache or even global memory. And so that's kind of when you start to read CUDA kernel code a lot, you will see this kind of pattern of moving data closer and closer to where the actual computation happens and identifying which data is the most important and used the most, and keeping that data as close as possible to your computation. Another concept that is also very important to understand is this idea of memory coalescing. So essentially, memory coalescing is this concept that allows us to exploit spatial locality. So in memory coalescing, we essentially want threads that are in warps to access data that is spatially local. So let's say we are doing some sort of vector op. We have a vector of elements that are operating on each other, and we have elements 0 through 31. So 32 elements, 0 through 31. We want a singular warp to be accessing each of these elements, and each thread is in charge of one of those elements. In this case, when one thread goes to access one of these elements, it's going to be automatically cached. And so when the other threads go to access the data they need, they don't have to go to global memory anymore. A better way of doing this would be to coalesce your memory accesses and then put them into a shared data block for your computation, or a tile. And we'll go into this later on in an example with matrix multiplication. But you'd store it in a tile and you would operate that. And you can actually do thread tiling. You can do warp tiling. There's a ton of tiling you can do to even further the efficiency of your data movement for your computations. And so this idea of latency hiding is making sure that our streaming multiprocessors are active at all times. Obviously, you cannot have full streaming multiprocessor utilization all the time. That would be very hard to achieve, but we can try. And this idea of having a warp scheduler that if a warp is stalling, we just get rid of it and we load in the next warp, allows us to kind of hide that latency. Warp divergence and reconvergence kind of has to do with conditional logic. Say we have 2 different execution paths that our threads can take. Half the threads are going to take one path, the other half are going to take another path. We're going to have to mask out the threads on one path as they execute. And essentially what that means is those threads don't execute that specific instruction. This way, our code is able to stay logically consistent. I have an example of some divergence right here. So essentially, what we're going to have here, so any index that is even is going to be multiplied by 2, and any index that is otherwise, we'll just add 1. So odd indexes, we'll just add 1. Even indexes, we'll multiply the data by 2. What will happen is all even indexes will execute this line, this instruction, and then we will mask out those threads and we will execute all odd indexes with this instruction. And then obviously we will sync the threads. But essentially what I would like to go over next is the tiled matrix multiply that I talked about earlier. What tiling allows us to do is allows us to take chunks of the data at a time and operate solely on that data in a given block in CUDA. And that block will be responsible for a certain block inside of the output matrix. And that block inside of the output matrix, we will go tile by tile and we will accumulate the final output values tile by tile. So when it comes to launching your kernel, there's some some hyperparameters that you can tweak. Your block size, how many registers you use. This goes back to like, do I do 1D thread tiling, 2D thread tiling? Do I do warp tiling? Whether you can do those or whether you can do those or you can't will depend on typically how many registers you have available. What should you do when you go to profile? Well, you should ask yourself a few questions. is the kernel memory bound or compute bound? Best way to do this, look at a roofline model. A roofline model is going to be your best friend when you're trying to figure out where your kernel is. Are all your memory loads coalesced and cached, right? You don't want to have uncoalesced memory accesses. You want all your memory access to be coalesced. That should be a very easy thing to spot and fix. And then lastly, do you have enough active warps to hide the actual latency of a lot of these global memory accesses? If you don't, then you're going to run into a lot of bottlenecks. And just kind of like a final thought, I guess. CUDA allows for performance at scale across obviously our modern computing domains. AI training and inference is the big one that people talk about, but also scientific computing and simulation. The biggest supercomputers in the world were initially built at major US labs to do massive physics computations, essentially. CUDA also allows you to do kind of real-time graphics and visualization. That will be it for today's video. I really appreciate you for sticking around for the entire video. If you could like and subscribe, that would really help me out.